Okay, sweet. Today I'm going to be talking about routing bugs. I think routing bugs are really interesting because a lot of time routing doesn't matter. But interesting enough, towards the start of this year, we saw quite a few hacks actually that related to routing. They came one after another. And in this presentation, I want to break down when routing actually matters and present some invariants that can help protocol developers as well as auditors find these sorts of issues. This is a pretty technical talk. Hopefully it will be relatively insightful if you look at code and need to think carefully about when routing actually matters. Quick about me, I studied OtterSec. We do smart contract audits. Most interestingly, we do audits across a very wide number of chains. So we look at EVM protocols, but we also look at Solana, Aptos, SWI, Fuel, Near protocols. And one thing that we noticed is that these routing bugs are applicable across multiple different chains. These issues apply whether you're looking at a Solidity lending borrowing protocol or a Solana one or an Aptos one. And that's why we want to do a presentation about it today because it's very broadly applicable. One of the first things that you should think about when you're writing a lending borrowing protocol is what actually matters, right? So I think broadly speaking, the invariant is that users shouldn't lose money. But this invariant is very ill-defined. I mean, what does lose money mean, right? Still, at the end of the day, everything kind of leads up to this invariant, right? Like the thing that actually matters in the end is users who have deposited some amount of money should be able to get that money back. A related invariant here is rounding, and specifically that rounding should be in favor of the protocol. When you have rounding, you can either round up or down, generally speaking. And one of these directions will give the protocol more money. The other direction will give the protocol less money. So you want to be careful and make sure that, generally speaking, you round in the direction that gives the protocol more funds. I think the last invariant that we'll talk about, and something that you'll see in the examples here, is that the value of a share shouldn't change. And this is a relatively ill-defined invariant because it does change through rounding, actually. But a lot of these attacks require the value of a share to be inflated or to change very drastically over a period of time. And one thing that will help is if we can prevent these shares from inflating in value. So these are the three exploits I'll be talking about. All of these happened over the course of 1 month, which is rather surprising. All of them iterated on the same idea, which was rounding of share values. This was a really cool vulnerability class because I think it demonstrated how hackers look at other hackers and they learn from them. After the Radiant Capital exploit, people saw and noticed that this was a new vulnerability class. And that's how they used the same ideas from that hack to apply to Wise Lending. And same for Abracadabra. I mean, these were non-trivial hacks, right? These Abracadabra ended up with $6.5 million stolen. If you were an auditor and you paid attention to the Radiant Capital hack, I think you could have stopped the other two. And actually one thing that we did as an auditing firm was after the Radiant Capital hack came around, we looked at it and we did a root cause analysis and we told all of our clients, this is something that you should be concerned about. This is something that you can patch. If you're an auditing firm or if you're an independent auditor, and if you've worked with lending protocols before, I think it's really important that you understand this exploit class and how it applies. Anyways, let's talk about the first one, which I think is also the most straightforward, Radiant Capital. There are 3 main steps here. The first one was they increased the liquidity index or the value of a share through flash loans. So essentially they donated a lot of money to the protocol. They borrowed against that. And in the final part, which is the most interesting, is that they exploited a share rounding error to steal money. And the interesting thing here is that the share rounding error was an off by 1, right? So it rounded against the protocol instead of against the user on that last step. But because the value of a share was so high, it actually mattered. So if we look at the code here, not sure or probably not familiar with the Radiant Capital code, but essentially this is the part where you can send a lot of money to the protocol, and then you'll update it into liquidity index variable, which stores the value of a share. And the idea here is that by donating directly to the protocol, you can inflate the value of a share far higher than what it otherwise should be. So I think in this case they used, I believe it was 2.1 million USDC, and then they had like around 1,000 shares or something like that. But the end result is that these shares were worth, an order of magnitude more than what they otherwise should be. It's a bit hard to see on the slide over here, but you can see how they do the donation. I think it is indeed 2 million. Yeah, and then the liquidity index gets updated to very, very high value. Yeah, so the second problem here was how Radiant Capital did rounding. And in this case, they rounded to the nearest integer. So you can see here they add half of b or half of the denominator, and then they divide, which in effect does rounding to the nearest integer. The issue here is that in certain cases you want to always round down, right? Like for example, if you're calculating how much shares that you should, or in certain cases you always want to round up. Like in this case, if you're calculating how much shares to take away from the user when they execute a borrow operation, you want to take away more shares than necessary. And in that case, you should be rounding up. But Radiant Capital made the mistake of rounding to the nearest, which allowed them to extract half a share. And if each share is worth $1 million, half a share is worth $500,000, which is quite a lot of money. I think the main useful takeaway here, and this is a takeaway that applies to the rest of the hacks as well, is that a single atomic share matters a lot, or can matter a lot, depending on the circumstances. And this is interesting because usually the rounding of an atomic token does not matter, right? So for example, if you have one atomic unit of USDC, whether or not you round up or down does not matter at all. And this is something as auditors we don't really pay attention to, or we purposefully ignore because it's not something that we need to care about. On the other hand, I think many auditors and protocol developers incorrectly assumed that because the value of a token is so small, or an atomic token is so small, the value of an atomic share is also very small. But that is, in this case, not true. And one of the implications here is that when you're designing your lending protocol, you have to think carefully, or really any protocol, you have to think carefully about when rounding matters, right? If you have an LP share, for example, the value of that share is not known. You might generally think that it should be quite small, but that might not be guaranteed. And if you can affect the rounding in a way that doesn't benefit the protocol, you can steal a lot of money from them. I think this was kind of the underlying broken assumption that allowed hackers to steal money from a number of other protocols. The second observation, which is useful here, but we'll see doesn't really matter as much, is Radiant Capital allowed users to send money directly to the protocol, and that allowed them to increase the value in the pool and change values of pool shares. If you're designing a protocol, you shouldn't let people do this. It's a pretty silly way to let people easily inflate the share value. Okay, let's move on to the next one, which I think is quite a bit more interesting. Wise lending. Very similar setup. They had a newly created pool, exactly one share. In this case, instead of sending tokens directly to the pool, they used looped rounding to inflate the share value. Again, shares are worth a lot. And the last part, which is also really interesting, was they had a double parsing bug. Hopefully people can see this slide. This slide is actually pretty important. You can see the amount that gets deposited and withdrawn at each interval. And you can see, hopefully, that the amount deposited goes from 3 to 7 to 19 to 55 to 163. So it roughly triples each iteration. And this happens because they're exploiting, or not exploiting, but they're using the intentional behavior of rounding to increase the value of a pool token. So you start with one pool token, is equal to, or one share is equal to one token. You do some rounding, then it becomes 1 to 3, then 1 to 7, 1 to 9, so on and so forth. And the interesting thing here is that this rounding is intentional. And if you didn't do this rounding behavior, it'd be a different bug. The protocol is forced to round in the pool's favor. Recall from the previous Radiant Capital example. But because it's forced to round in the pool's favor, people can also use this behavior to inflate the value of a share. And to be clear, this by itself is not necessarily a bug. The increased value of a pool share does not necessarily mean that you can exploit the protocol. It just makes it a lot easier to. And in this case, we can see how it actually does that. So I think the critical vulnerability for wise lending is this double parsing bug. And actually, as I was writing these slides, I saw this really nice tweet from Daniel VF. So credit to him for this observation. But the crucial idea here is that you have two different implementations processing the same input. So the first one they had was a simulation or a check that saw if the borrow amount was proper, and that ran on the token amount. Unfortunately, the actual borrow operation operated on the share amount. So because they were operating on two different amounts or two different units, when they converted that token amount to the share amount, that resulted in a double parsing vulnerability and allowed, in this case, the user to borrow more than they should have. Sweet. Let's see. Yeah, so I think there's two main takeaways here. The first one is that even without direct donation, the share price can still be inflated. And I think this is a really important takeaway because it forces you as a designer of lending protocol to think carefully about what you can do. And in this case, remember again that this share price rounding is necessary. Like if you round it in the other direction, it would be a different vulnerability. So you can't just change the rounding direction here. You have to do something a bit more creative, which we'll talk about in the mitigations part of this presentation. I think the second one is that even though the rounding was done correctly in all cases here, the checks were done incorrectly. And that was because they had two different checks. The first check was on the token amount for how much they can withdraw. And the second check was during the actual borrow, where they converted it to shares. Okay, the third example that I want to cover would be Abracadabra. This is the last one, and I think it's probably the most interesting. 4 main steps again. The first part is that this did not start with an empty pool. So there were users in this pool, which made it more easily exploitable. I think the previous hack-wise lending required you to start with a newly initialized pool. So they first repaid off debts for users, and this deflated the share value. This is different from other hacks because all the other hacks increase the share value. So that's the first thing that is pretty interesting, hopefully. The second is they, again, repeatedly borrow and repay using rounding until the number or the amount of liquidity is 0. And the third part, and this is actually a very common broken assumption, is that in their share to asset calculations, and I'll pull up the snippet of code later, they have an incorrect assumption that the ratio of assets is 1-to-1 when the number of tokens is 0. And you'll see this a lot actually when you have token to share conversions, where to avoid a divide by 0, for example, people will have like an if number of tokens equals 0, return 1. That's sort of like a default initialization value for the pool ratio. But this is actually incorrect when you have outstanding shares. And the last part is, because of this broken assumption, they were able to mint themselves a far higher number of shares than they otherwise should be, and they were able to steal money from the pool. Yeah, so the first part of this is probably, not super, not a great feature. For some reason, Applicability let you repay for other people, which, is okay, but also is like a pretty big attack surface for no reason, right? Like, come on, let's be honest. We're not altruists here. I'd be surprised if this function was used ever, actually, aside from this hack. Generally, people don't repay debt for other people. If you want, you can have like a socialized debt feature or bankruptcy feature, but in this case, permissionless repaying for even healthy accounts is a pretty big stretch. And in this case, this is actually a critical part of the vulnerability because it allowed the hacker to repay the debt for other positions, making it so that there was very little debt left, while there's still a very large number of shares, which deflates the share value. You can see here, they go through and they repay a bunch of debt for people. Really nice guy. The second part, or let's see. So the second part is where they borrow and repay in a loop to do the last, or to get elastic to zero, or elastic is the number of tokens. And again here, they are rounding correctly, and that's the interesting part, right? It's like, aside from Radiant Capital, the other two hacks, or all the other hacks in this presentation, all have correct rounding behavior. So even if you have correct rounding behavior, you might still have a bug. And you have to think beyond just, am I rounding in the correct direction or not? So here you can see, and this is similar, or vaguely similar to the share inflation for wise lending. You can see they borrow and repay in a loop. And I think this is the last and the most interesting part, where the code, and this is, again, very common code, if the amount of elastic tokens is 0, they set base equal to elastic, or in this case, they say the number of shares that you get is equal to the number of tokens. So essentially this says that if you have no tokens, the token to share ratio is 1-to-1, which is not true. And actually this code is really common. Like if you read lending protocol code, oftentimes they will have this default initialization case where if either tokens is 0 or shares is 0, they kind of assume that the other is 0 as well, and the protocol is uninitialized. But you have to be very careful here, because if you can get either tokens or shares to 0 when you don't expect it, like in Applicability, you can end up giving yourself a lot more shares than you expect. And I think that's what they did here. They minted, I think on the 5th line, they minted themselves a lot more shares. I think there's two main takeaways here. The first one is that you should think carefully about what features you want. In this case, permissionless repay, was a nice feature to have, but probably shouldn't have been included. It's also something that people aren't going to use, right? Maybe from a permission sense, in the sense that you as a protocol want to pay down the debt for bankrupt positions, but it's otherwise a pretty dangerous feature to have. The second is that when you have share conversions, you should think carefully about your default case. And just because your token or shares amount is 0 does not mean that the protocol is newly initialized, or does not mean that the share value or the share ratio is 1-to-1. Okay, some mitigations. I think the first one is probably the most effective, and this is the one that we recommended to our clients, is to have a minimum deposit. And the reason for this is that if you have a minimum deposit, it becomes a lot harder to mess around with the amount of tokens or mess around with the share value, because you have to also mess around with other people's share values, right? Like if you inflate the value of a share by 1,000 times, for example, you need to inflate everyone else's shares by 1,000 times as well. And that means donating them free money, essentially. This makes it quite a lot harder to execute any sort of exploit. The previous exploits, like wise lending, for example, required a new pool. And the reason they required a newly initialized pool is because otherwise they'd be unable to manipulate the share value up so high. The second one, which I think is pretty straightforward as well, is you should think carefully with the rounding direction when you convert between shares and assets. And this is kind of table stakes at this point. You should specify whether you're rounding up or down. The third one, which is more interesting and depends on your protocol design, but some protocols we've seen store the conversion rate separately between shares and values. So they don't store it as shares divided by values, and they don't calculate it dynamically. But they store it separately as a different variable. And I think that can also make manipulation a lot harder. So this is Uniswap v2 code. Essentially, they subtract out the minimum liquidity number of shares. Pretty easy patch. You can apply the same thing to your Lightning protocol as well. This is the rounding code. I forgot where we pulled this from, but yeah, you should take in a rounding direction when you convert between shares and amounts. And the third one is a bit more interesting. This is from a protocol that we audited. But yeah, you can store the interest factors separately. In this way, you don't need to dynamically construct the share to token ratio. You can just pull it from a variable. It also makes it a lot harder to change because you only increment this variable, or you only change this variable on interest accrual. Some general takeaways here. I think the first one is, and this goes back to the wise lending hack, but instead of attempting to reason about effects after a state change, you should apply the state change and check the invariant. And this actually applies more broadly. I think this is a really good takeaway, not just for rounding bugs, but in general. It's a lot easier to, if you have an invariant that you know must be true, just like do a bunch of stuff and check it afterwards, right? So for example, for Lightning protocols, a really good one would be position health. You can let the user do whatever they want as long as you know for sure that you have a position health check afterwards. And that's similar to what flash loans do. The second one is that user operations are always denominated in shares, not tokens. And your accounting logic should think in terms of shares whenever possible. Again, the wise lending hack was because they took tokens and they checked if the number of tokens that they withdrew was correct, but they didn't convert it to shares beforehand. The third one, and this one's the most tricky, is that you should try to think about correct rounding behavior whenever possible. And I say this is tricky because, come on, rounding comes up everywhere. Like every time you do division, you have to reason about whether that rounding is correct, in theory. But that's a lot of cognitive overhead. I think that as an auditor, you should be careful, or auditor or protocol developer, you should be careful and you should think about when does it actually matter. And it might matter in more ways than you think, right? It might matter not just for shares, but for share-like things. Before we thought that it didn't matter for shares, but clearly it did. Sweet. This presentation was based in large part on a blog post that I wrote. I would recommend checking that out if you prefer reading. Otherwise, open to questions.